This video is a quick summary of elastic moduli for the purpose of studying sound waves in materials. So the main point is that we're going to study Young's modulus, which is related to the propagation of sound waves in a thin rod, and the bulk modulus, which is related to the propagation of sound waves three-dimensionally in a material. In fact, we're already very familiar with an elastic modulus. The spring constant of a Hooke's law spring is the simplest example. And if you recall, that basically measures how stiff the spring is. So over here on the left, we have a diagram of a Hooke's law spring. In the top picture, it's just sitting at its natural length, and we call that x equals 0. And then we apply a force, and we compress it through some distance x from its natural length. So we're going to keep returning to a phrase that's worth remembering here, and that's stress causes strain. By a stress, we mean a force or a pressure exerted on the material. And by strain, we mean the deformation of the material. So in the case of a simple Hooke's law spring, the stress is the force F. And the strain, that's the resulting deformation through a distance of x. And those are related by Hooke's law. That's just F equals kx if we ignore the minus sign for a moment and just look at this as a relation between the magnitude of the force and the magnitude of the compression. So there's a stress, that's F, causing a strain, that's the x. And that k, again, is a measure of the stiffness of the spring. If k is bigger, then it takes a bigger force to get the same compression x, or we could say the same force causes a smaller compression if k is bigger. So solving for k, that's F over x, or stress divided by strain. And that's our first example of an elastic modulus. And all of our elastic moduli will have this same basic form of stress divided by strain. It's just a matter of finding a useful way to define the stress and the strain in each context. So we move on to the case of a thin rod, and we're trying to define stress and strain in a practically useful way here. So we start with a rod of length L and cross-sectional area A, and we exert a force at both ends to compress this thing by an incremental amount that we call delta L. Note that we call the force F perpendicular, since any off-axis component would cause the rod to spin or move vertically, and we have to apply this force at both ends, otherwise the rod would just take off accelerating horizontally. So what's a good way to define stress for a thin rod? A simple force isn't going to work because a thicker rod should have less deformation for the same force. We need something that scales with the thickness of the rod. And that's actually pressure or force per unit area. So this way, if we're looking at a rod with twice as much cross-sectional area and we apply twice as much force to it, that gives us the same stress on the material. And just to look at the units of this stress real quick, recall that pressure is defined as force per unit area and is measured in newtons per square meter or pascals. So what we're talking about for our stress here is actually pressure. So what about the strain? We can't just use a simple change in length here because a longer rod is easier to stretch or compress by a given absolute amount. To understand why, I think it's easiest to think about the stretching case and just imagine two wires. We'll make one of them have a length of L and the other a length of 2L, but they have the same cross-sectional area. The same force is going to stretch the longer wire twice as far because what's really happening at the microscopic level here is that we're stretching intermolecular or interatomic bonds, and with the same force applied, every one of those particle-to-particle bonds feels the same force in either case and experiences the same amount of stretching. So the wire is going to stretch by the same percent in each case, which means a longer wire will have a larger amount of total stretch. Or in this case, because the longer wire was twice as long, it gets twice the stretch. So how do we define strain in a practical way? What we need is a fractional change in length, delta L divided by L. Now we go back to our old saying, stress causes strain, and we write a formula just like Hooke's law. There's our stress on the left-hand side, and we see our strain, our deformation on the right-hand side, which we decided should be a fractional change in length, and the constant of proportionality there, that's called Young's modulus. So solving for Young's modulus, we get the definition y equals F perpendicular divided by the cross-sectional area all divided by the fractional change in L, so delta L over L. And since the denominator is unitless here, we see that Young's modulus is measured in units of pascals. So let's work a quick Young's modulus example with a stretched wire. So in our example, we're told we have a 32 gauge steel wire, and we're told what that means in terms of diameter. That's 0.202 millimeter diameter. It has an initial length of 2 meters, and we're told the Young's modulus for steel is about 20 times 10 to the 10th pascals. So we're going to hang a 5 kilogram mass from the end of this wire, and we want to compute the change in length. So first we go back to our basic sort of Hooke's law kind of idea. Stress causes strain. And the way we're going to measure stress is the force applied at each end of this wire divided by the cross-sectional area. Young's modulus is the constant of proportionality, and the strain is a fractional change in L. And our goal here is going to be to solve for delta L. So we can just do this symbolically before we get into the physics. Delta L is going to be F perpendicular times the original length L, divided by the cross-sectional area times the Young's modulus for steel. And we have to do a little bit of force analysis here. We have a 5 kilogram mass hanging off the end of this wire. So we need to figure out the weight of that thing. And then we know the weight of it is balanced by the upward tension in the wire because nothing is moving here. Okay, so there's our downward pointing weight vector, and that has a magnitude of mg. And with a mass of 5 kilograms and using an approximation of g equals 9.8 meters per second squared, we get a weight of 49 newtons. Again, the mass is in equilibrium here, so the upward tension of the wire pulling up on this mass must have the same size as the weight of this mass, so that's also 49 newtons. All right, so now we have F perpendicular. Each end of this wire is going to feel a force of 49 newtons. And we're ready to just go ahead and plug into our formula here. So to get the stretch length, I need the perpendicular force. That's 49 newtons. And then we multiply by the original length of this wire, which was just given to us as 2 meters. Then I need the cross-sectional area, and that's pi times radius squared, but radius is half the diameter. And when I square that, I get a factor of 1/4. So I can write this as 1/4 pi diameter squared. And we were given the diameter as 0.202 millimeters, which in SI base units is 0.000202 meters. And then we have to put in our Young's modulus of 20 times 10 to the 10th pascals. And when we run the numbers on this to 3 significant digits, we get 0.0153 meters. And it might be nicer to express that in centimeters as a stretch of 1.53 centimeters. And that seems like a pretty reasonable answer here. We have a slight stretch of 1.5 centimeters when we hang 5 kilograms off of this wire. So now we move on to bulk modulus, and that measures the stiffness of a three-dimensional material being compressed from all sides. So in our diagram here, we have an object with an initial volume of V. We then exert forces from all sides on it to squish it, and it shrinks by delta V to some new smaller volume. And again, we think about what's the practical way to define stress here. And we want something that scales with the size of the material, and pressure is again a reasonable way to define it. So the stress we're talking about is actually a change in pressure causing a change in volume. So that's going to scale with the size of the object. A larger object is exposing more surface area to that pressure, so it's exposed to a greater cumulative crushing force. And of course, the units of pressure are pascals. So what about the strain here? An object with twice the volume should compress twice as much under the same change in pressure. Again, we're just visualizing equal deformations of interatomic bonds over an object twice as large. So we're going to use a delta V over V for the strain or deformation of the material. And again, we just write down the equivalent of Hooke's law. Stress causes strain. And this time, that's delta P for the stress, and then the strain is a delta V over V, and our constant of proportionality there is called the bulk modulus. Note that we put in a minus sign because an increasing pressure should correspond to a reduction in volume, but you could also just state this rule as a relation between magnitudes if you liked and just get rid of the minus sign. So solving for the bulk modulus, we get a formula for the bulk modulus as negative delta P divided by the fractional change in volume, delta V over V. And again, the units of bulk modulus are going to come out to pascals because the denominator is unitless here. So we're going to wrap things up with a simple example of how to apply the bulk modulus. So in our example, we're asked to find the percent compression of seawater at 2,000 meters under the surface of the ocean. We're told the density of seawater, that's about 1.03 times 10 to the third kilograms per cubic meter. And the bulk modulus for water is about 2.18 times 10 to the ninth pascals. Now, many of you may have been told that liquids are literally incompressible. I know I was when I was a student. And this just isn't true. Liquids are compressible, but they are incredibly stiff. So if you remember from our study of hydrostatics, we can think of pressure as energy density. So if we're talking about a liquid under high pressure, there's a bunch of energy stored there. And there's no mechanism to store energy unless that liquid is actually compressible. So what we're doing is compressing incredibly stiff intermolecular springs, and those are actually electrostatic in nature. And we can store an immense amount of energy in the compression of a liquid, but it's barely going to compress at all. Well, this stress causes strain idea in the bulk modulus, it's going to allow us to actually compute that microscopic compression of a liquid for the first time. So if we write down our basic stress causes strain equation, again, the stress we're talking about is a change in pressure as we go from the surface of the ocean down to 2,000 meters deep. And we'll go ahead and keep the minus sign version of this for now. That's equal to the negative of the bulk modulus. Again, that's equivalent to a spring constant. It measures the stiffness of the liquid. And we can already see just qualitatively, that's a really big number. So liquids are very good at resisting compression. And then our strain, that's the fractional change in volume. And that's actually what we're trying to solve for here. So we can solve for delta V over V. That's going to give us a fractional change in volume, and then we'll convert it to a percent at the very end of the problem. And this is given by our change in pressure divided by the bulk modulus, and there's a minus sign in front, which is simply going to indicate that the liquid is getting smaller instead of bigger. So now we have to appeal to some of our experience with hydrostatics and find the change in pressure when we go to a depth of 2,000 meters beneath the surface of the ocean. So a quick side calculation here. Remember the change in pressure as we go to a depth of d beneath the surface of a liquid is given by rho times g times d, where rho is the density of the liquid, d is the depth. And of course, we were given the density of seawater, 1.03 times 10 to the third kilograms per cubic meter. Incidentally, that means every cubic meter of seawater has 30 kilograms of salt dissolved in it. It's a surprisingly big number. Now G, we'll keep using the crude approximation of 9.8 meters per second squared, and then our depth is 2,000 meters. And when I run the numbers on this, just keeping a little extra precision for now, I get 2.019 times 10 to the seventh pascals. So that's our increase in pressure as we go 2,000 meters beneath the surface of the ocean. So we'll go ahead and plug that in, and then we'll plug in our bulk modulus for the seawater. And this gives us a result of about negative 0.009. Now again, the minus sign just means we're talking about a compression instead of an expansion. And this number rounds to about 0.01. So if we're going to express this as a percentage, we can say the compression of seawater at a depth of 2,000 meters is about 1%. So that's another reminder that although liquids are compressible, they are incredibly stiff. So we're talking about immense pressure 2,000 meters below the surface of the ocean, and we only get about a 1% compression of the seawater down there. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.